In this talk, I present Hoof, a wrist-run sensing method that allows VR users to interact with virtual objects even if they happen to be outside the headset's tracking field of view. I worked on this project together with Rayan, Armani, Cheng, and my advisor Christian Holz at ETH Zurich. User interface in current virtual reality systems is increasingly designed for direct interaction using our hands. Because the headset tracks hands using cameras, this limits the input range to the field of view. As a result, most interaction in VR is designed for visual control. This, however, prevents users from interacting with virtual objects that happen to be just outside the current visual area, even when they're close by and conveniently accessible. Current systems require users to first bring these objects into view before being able to access them by hand. Hoof allows VR users to interact with objects outside the field of view. We show Hoof's benefits in 3 demo scenarios. In our first demo, the user can grab building blocks just outside his field of view but within his proprioceptive reach, while keeping his view focused on assembled construction. In this bow and arrow demo, Hoof extends the range of input to allow the user to use the bow as they would with controllers. Finally, by tracking the hand position and orientation around the user's whole body, Hoof provides an improved Beat Saber gaming experience even without controllers. Our method only requires signals captured by a 6-axis IMU placed at the wrist to estimate the 3D hand position, 3D orientation, as well as to detect pinch input. The IMU is integrated in a sensing platform that includes a battery and a BLE module, which allows for wireless use. A built-in haptic actuator renders feedback in response to detected input events. As long as the user interacts within the field of view of the headset's cameras, the position and orientation of the head and the hands are tracked by the VR system. When the hands leave this tracking space, Hoof continues to estimate the user's wrist pose. For this, it takes the last 5 available hand and head poses from the VR headset before the hands left the tracking range as input to initialize the tracking trajectory. It then predicts the current 60 hand pose based on the streamed acceleration and angular velocity signals from the IMU and the headset's ongoing head tracking. The pose estimator consists of a novel temporal neural network architecture. The within-view hand and head poses are processed by a 2-layer recurrent neural network. We estimate the wrist orientation from the IMU signals using an extended Kalman filter. The signals are then downsampled by a factor of 8 using a convolutional neural network with max pooling layers and fed as input sequence to a transformer. We prepend the output of the RNN as initial token and add a positional encoding. For each transformer output, we predict the position and orientation of the wrist through a series of fully connected layers. We train our network with supervision. We use a L1 loss on the estimated 3D wrist position, as well as on the estimated orientation, which we predict in a 6D representation to ensure continuity. To detect pinch events, we use a running rate of change score, which accumulates the absolute change in acceleration across time. Pinch events cause sudden changes that lead to a strong increase in the score function and in this way can be detected through a threshold. To refine the pinch position, we apply a 15 cm offset along the forearm. We conducted 2 user studies to quantify the accuracy of Hoof as well as participants' performance interacting across on and off-screen targets. In both studies, participants wore an Oculus Quest 2 VR headset and our Hoof wristband. For reference, we used an 8-camera object system and optical markers that each participant wore on their shoulders, arms and wrists. For our first study, we recruited 12 participants who performed 3 different tasks. In the Oculus condition, participants relied solely on the Quest 2 headset to track the hand movements, which required them to turn the heads to keep the hand within the camera's field of view. In the grab task, participants had to retrieve one of 17 spheres placed next to them. In the drop task, they had to drop a sphere into one of 17 drop zones. In a compound task, participants repeatedly switched between retrieving and placing objects. In the optical condition, participants were instructed not to turn the head and to look straight ahead. During this condition, we used the OptiTrack motion capture system to provide the VR environment with the participant's wrist position and orientation data, permitting an analysis of the human ability to interact based on proprioception only under nearly optimal tracking conditions. Using the OptiTrack ground truth data, we were also able to train Hoof and evaluate its performance in a 6-fold offline cross-participant evaluation. In our second user study, we recruited 10 new participants who performed the same 3 tasks using Hoof in an interactive real-time evaluation. For comparison, they also completed the same task in the Oculus condition. We evaluated success rates across trials for all conditions in both studies. Participants had a success rate of 95% when interacting under visual control. Under near-optimal tracking conditions, participant success rate dropped to 18 out of 20 trials when interacting purely based on proprioception. Of these 18 successful trials, approximately 17 interactions were correctly detected using Hoof without any external infrastructure or cameras. We also measured trial duration across all conditions. Our study found that outside field of view interaction resulted in lower mean completion times. For both studies, participants preferred the condition without the need to turn their heads to bring off-screen targets into view. Outside field of view interactions mostly occurred within the first 3 seconds, during which Hoof achieved the best tracking performance. Hoof's tracking also remained stable afterwards, where the median and mean position error does not significantly exceed 15 cm. This indicates that Hoof has learned to make robust position estimates over longer durations, considering the natural anatomical constraints of the human body. Hoof is not directly comparable to other methods that estimate the wrist position from a single eye view, because we evaluated our system on a novel dataset and in an interactive setting. Compared to previous methods, Hoof also receives the initial position of the hand as input. However, Hoof's relatively small median position error of 7 cm demonstrates the strength of our estimation pipeline to handle the accurate estimation of the wrist pose over short periods in stationary settings. In summary, Hoof enables more intuitive and natural interactions with AR and VR environments by leveraging user proprioception in the outside field of view space. It also has the potential to optimize the form factor and power consumption of future AR and VR headsets by outsourcing some of the computation to other devices. In the future, Hoof could also potentially support hand tracking interaction inside the headset's field of view, reducing the computational cost of computer vision-based processing.